This video is on solving exponential, logarithmic, and logistic equations and answers the essential question, how can logarithms be used to solve exponential equations? In particular, this video we're going to talk about financial math. Now, if you were to receive a $10,000 check in the mail, the question I want to pose is, would you choose to invest that money in a high-yield savings account, which offers 3.7% interest every month? Or, on the other hand, would you choose to go and invest your money in a CD that pays a higher percent interest once per year? So in an investment, you want as high a percentage of interest as possible, but you also want that interest to compound as often as possible. So in the first example, we see a lower percentage rate, but a more often compounding of that interest. In the second example, second option, we have a higher interest rate here that compounds less often. So which is the better of the two options? Let's explore that in this video. To begin with, let's look at the formula for what it looks like when interest is compounded k times per year. K times per year meaning annually. We have k equal to 1, that's 1 time per year. Biannually would be 2 times per year, so k would be 2. Monthly, we would have k equals 12. I skipped quarterly. You might see quarterly. Quarterly, every quarter, that would be 4 times per year. Monthly, we did weekly. How many weeks are there per year? K would be 52. Daily, typically banks will operate on a 365-day year, so daily would be 365. So those are some examples for k times per year. In the formula for calculating the amount of money that has been invested at a certain annual percentage interest rate, with the interest compounding k times per year, follows the formula A equals P times the quantity 1 plus R divided by K. That entire quantity raised to the K times T power, where the A represents the amount of money after T years. P is your principal, where that's another way of saying your initial investment. That's in dollars. The amount of money, this is also in dollars. R is your annual percentage interest rate. And K, as the title explains, and as we've already talked about, is the times per year the interest compounds. So that's our formula for the amount of money where your interest is compounding k times per year. So we're going to think about that formula when we go back to our previous example and try and debate or compare which of the two options of investments is a better option. So revisiting this problem, we have two situations. So we'll look at both of these separately and compare the results. We are investing a principal amount of $10,000. And in the first case, our annual percentage interest rate R is 3.75%, which corresponds to the decimal 0.0375. That interest is being compounded every month, so our K is 12 monthly compounding interest. In our second example, we're investing the same amount, $10,000 principal, and this rate is 4%, so the decimal version of that R is 0.04, and the interest is compounding only once per year, so the K in this case is 1. Now what we need is an amount of time to compare the two investments. So if we just decide on some amount of time to invest these, and then we'll compare the results, which earns us more money. So let's say we invest over 20 years, we'll say. So we're going to choose 20 years in both cases. We'll calculate how much our investment is worth after 20 years and decide which of the two accounts is the one that we want to invest in. In the first case, our amount is going to be A is going to be equal to 10,000, our principal, times the quantity 1 plus R, which is 0.0375, divided by K, all raised to the K times T power. So we substitute all of our quantities in, we put that into the calculator and end up with a result of $21,145.25 if we round down and don't give ourselves more money than we've earned. So that's the first case. The second case, we're going to set that up in the amount that we earn with $10,000 principal investment times 1 plus, now this interest rate, 0.04 divided by 1, all raised to the KT power, which is just 1 times 20. When we input that into the calculator, we get an ending amount of $21,911.23. So comparing the two quantities, given the same amount of time investing the second option, the higher interest, compounding less frequently in this case, is the better investment because we'll end up with more money over time. And as I said before, the best situation is if your interest can compound as frequently as possible. The more frequently compounding interest, the more money you're going to earn, to the point where if we could compound our interest an infinite number of times per year, if it's continuously compounding, that is going to be our best scenario. And the formula for continuously compounding interest, if we consider K approaching an infinite value, takes on a slightly different form than the previous formula, and this looks like A equals our original principal times the quantity base E raised to the R times T power. Looks like the word PERT, the PERT formula. And again, the quantities are the same. A is the ending amount that we saw before, ending amount of money after T years. P again is our principal. Which is dollars. R is your interest rate, our annual interest rate. as a decimal, and then t is the time in years of your investment. So this actually will result in an even better scenario than either of the two previous examples. If we look at that same amount of principal that we just saw a second ago, the $10,000, and if we were to look at either of the interest rates, the 3.75 or the 4%, if we continuously compound the interest, we'll end up with an even better return on our investment than interest that's compounding only a certain number of times per year. And so the two formulas that we want to remember, this is the one formula for continuously compounding interest, and then we saw the previous formula for interest compounding k times per year.